All right, today we're going to break down an algorithm that's more than just code. It's really a fundamental law of computer science. We're talking about merge sort, and we're going to get into the anatomy of why its famous performance isn't just fast, it's a mathematical certainty. I want you to just let that sink in for a second. Inevitable. That's not a word we usually associate with code. It suggests a kind of structural power, a confidence that goes beyond just being clever. You see, merge sort doesn't play games. It couldn't care less if your data is already perfectly sorted, a complete train wreck, or totally random. The process it follows and the time it takes is always the same. It's a rock-solid guarantee. So if its performance is a guarantee, what's the secret sauce? Let's peel back the layers and see what makes this thing tick and how it earns its reputation as an absolute cornerstone of computer science. The whole strategy is right there in the name. Divide and conquer. It's a super powerful idea. If a problem is too big to handle, don't bang your head against the wall. Just break it down into smaller, bite-sized pieces until they become so simple they're already solved. Then you just build the solution back up. And that's it. That is the entire playbook. Divide, sort, merge. There are no special if statements, no weird edge cases, no clever hacks. It is pure, relentless structure. And that's exactly where its power comes from. Okay, so first up, the division phase. This is where we start breaking the problem down. And you might think this is a lot of work, but as you'll see, it's actually the cheapest part of the whole deal. It's practically free. So the goal here is dead simple. Take your list of numbers and chop it in half. Then take those halves and chop them in half. You just keep going, again and again, until all you're left with are a bunch of tiny little lists with only one number in each. And this right here, this is the logical linchpin for the entire algorithm. It's the base case in recursion. I mean, think about it. A list with only one thing in it is, by definition, sorted. What else could it be? The problem, at this tiny scale, is solved. And what's wild is how cheap this phase is. We're not actually comparing any numbers here. We're not swapping any elements around. All we're doing is finding the middle of a list. Computationally, that's nothing. It's just slicing. And it sets the stage perfectly for what comes next. Okay, and now we get to the magic of the conquer phase. This is where you have to put a little bit of faith in recursion. The algorithm isn't trying to sort the whole giant array at once. Nope. It's just taking two of those tiny, already sorted lists and merging them. It trusts that the smaller problems have already been taken care of. Which brings us to the merge. If the dividing phase was the free setup, this is where the methodical, honest-to-goodness work happens. This is where order is literally constructed out of all those little pieces. The process is super straightforward. Imagine you have two small, sorted stacks of cards. You just look at the top card of each, pick the smaller one, and put it down to start a new, bigger, sorted stack. You just do that again and again and again. So let's just walk through it. We've got our two sorted arrays. We look at the first elements, 4 versus 2. Well, 2 is smaller, so it goes into our new array. Now we compare 4 and 9. 4 is smaller, it moves over. Now it's 8 versus 9. 8 moves. See? It's just a simple, repetitive set of comparisons. And notice what isn't happening. There's no guesswork. The algorithm never has to second-guess itself or go back and undo a decision. It's a one-way street, just methodically building a bigger sorted list from two smaller ones. Okay, so we've seen the divide and the merge. Now for the big payoff. How do these two simple actions combine to give us that famous, and I mean guaranteed, O(n) log n performance? Well, it's not an estimate, it's just math. So, fact number 1 comes from the divide phase. If you have a list of n items, how many times can you chop it in half before you get down to single items? Well, that's literally the definition of logarithm base 2 of n. So, the number of levels in our process is log n. Simple as that. Now for the other piece of the puzzle. Think about any single level of this operation, whether it's at the top, where we're merging two huge lists, or at the bottom, with tons of tiny pairs. If you add up all the elements being touched on that one level, the total is always n. Every element gets processed once per level. And that's it. You just multiply those two unavoidable facts together. We do n amount of work at each level. We have log n levels. Boom! N times log n gives you O of n log n. It's not a guess, it's just arithmetic. And here's the beautiful result of that math. Best case performance, O of n log n. The absolute worst case, still O of n log n. Average case, you guessed it. The algorithm just doesn't care what the input looks like. The path it takes is always the same. And you have to realize, for a lot of real-world systems, that isn't a limitation. It's the entire point. It's the main feature. Sometimes raw speed is great, but a lot of the time, predictability is king. But of course, no algorithm is perfect. This mathematical purity comes with a price tag. On the plus side, it's stable, predictable, and even easy to parallelize. But it has a big limitation: memory. To do that merge step, you need to create a whole new array, which means it requires extra space. It's not in place. And that's just a fundamental law of engineering, right? You're always making a trade-off. With merge sort, you're trading memory. You're spending extra space in exchange for a guaranteed, predictable runtime every single time. Which brings us right back to where we started. Merge sort isn't trying to be the smartest algorithm in the room. It doesn't need to be. It wins because its logic is just so sound, so structural, that its efficient performance is simply unavoidable. So I'll leave you with this question. We're all obsessed with making things faster, right? We love to talk about the best case scenario. But where else, in technology or maybe even in life, is knowing the worst case outcome actually way more important? Where is that guarantee, that predictability, the one thing that truly matters?